Welcome back to our course on mechanical behavior of materials part 2. So in the last lecture, we discussed about the mechanisms for fatigue crack propagation, and then we also quantified it in terms of dA by dN versus delta K plot, right? And the plot looks like this. So we have dA by dN on y-axis and delta K on x-axis. Both are in log scale, okay? So it goes from stage 1 to stage 2 to stage 3, and stage 2 we can use Paris law equation, right? Which is dA by dN equal to C delta K to the power M. So this N here is can be denoted as M, and for most metals I told it varies from 2 to 4. Okay. So now let's see if I give you the configuration of the sample, and then I ask you what is the number of cycle for a length increment, say A1 to A2. How do we approach that kind of problem? Okay. So suppose you are performing a test on, say, infinite or semi-infinite SENT specimen. Okay. And what is the Y value for semi-infinite SENT? We had discussed that is 1.12. Okay. And the test is being done under constant applied stress, that is delta sigma is say 140 MPa. Okay. And the Paris law behavior is like this: dA by dN, that is in meter per cycle, given 0.66 into 10 to the power minus 8 delta K 2.25. Okay, where you know what is delta K, right? So what you have to calculate is the number of cycles for crack to grow, right? Say from A1 to A2. Some values of A1 in millimeter to A2. Okay. So this is the problem. So how do we solve it? Okay. So let's do that. So we know delta K is given as Y sigma root pi A. Y in this case is constant because this is semi-infinite SENT plate. Okay. And dA by, so now I am making it a general equation rather than the exact equation given in the question I just mentioned. So this is C delta K to the power M. Okay. So now we can write this equation as dA by dN. Now let's use delta K, whatever is here in this equation. So Y sigma root pi A to the power M. Okay. And then we can write dA by, I'm bringing A to the left side. So this becomes AM by 2 CY sigma. Okay, and now it will be delta sigma, right? Because delta K is, so here it should be delta sigma. Okay, so delta K is, since this is 40, delta K is Y delta sigma root pi A. We have discussed that. Okay, so here you are left with now this, and then there will be factor of root pi also. And so let's see, root pi to the power M. And also this to the power M. Okay, so now we can write dA by AM by 2. It is moving from A1 to A2. Okay, so crack is growing from A1 to A2. You have to calculate what is the total number of cycle. So this we can write Y delta sigma root pi to the power M and then dN. Okay, and this dN is the total number of cycle for increment of length from A1 to A2. Okay, and then if you solve it, it will be A minus m by 2 plus 1 minus m by 2 plus 1 goes from A1 to A2, and right side remains like this. And so n will be now A2 1 minus m by 2 minus A1 1 minus m by 2 divided by 1 minus m by 2, and then C y delta sigma root pi to the power m. So this is the number of cycle you will need for a track increment from A1 to A2. Okay. So it is in terms of y delta sigma. So if I give you a question where you know the configuration, so you know what is y. Okay, delta sigma will be say also given, so you know what is delta sigma. And if it is following Paris law, so based on the equation, you know what is m, right? So in the previous question, m was 2.25 here. Okay, and C is 0.66 into 10 to the power minus 8. Okay, so if all these values are given, you have to use this equation to find out what will be the number of cycles for track increment from say A1 to A2. Okay, so this is how you approach the problem, and this type of problem will be also given in the assignment. Okay, now let's come back to the mechanisms and factography. So we have already discussed about fatigue crack initiation and propagation, right? So now let's talk about factography, where we will also discuss about uh, striations I mentioned in the last class, right? So typical fatigue failure will exhibit the following features. I will draw the schematic, and at the end of this lecture, I am going to show you all the factographs, okay, or factographs, okay, of all those features. So first, there will be a distinct nucleation site for fatigue crack. Okay? Distinct crack nucleation site, okay, or initiation, right? So if you see the fracture surface, you should be able to locate a distinct crack nucleation site from where fatigue crack has initiated, and from there it is going to propagate. Okay. Now there will be smooth zone after initiation. And this will be related to crack propagation. So you're going to see, if you see the fracture surface, macroscopically, you will see some smooth surface just after initiation. That will be related to the crack propagation path. Okay, a crack propagation surface. There you are going to have two type of features typically. One is beach mark. Okay, this is also known as camshell mark. Okay, and this will indicate. So as soon as you see beach marks on the surface, this indicates that load has changed during the service, or it has stopped. The fatigue cycle has stopped during its service. Okay? So this indicates that load is changed during service or load is intermittent. Okay, so that is one mark you are going to see, one feature on the fracture surface, and these are macroscopic in nature. You should be able to see it, okay, very clearly. These are macroscopic features. Now, second one is striations, and these are microscopic features. Okay, so these are small ridges that are perpendicular to the crack propagation direction. Okay, and second, these are on a much finer scale and show the position of crack tip after each cycle. And finally, you are going to end up getting distinct final fracture region. And this will be rough zone. Okay. So if you see the fracture surface, macroscopically, you are going to observe one nucleation site. From there onward, you are going to see smooth zone, which will be related to the propagation, fatigue crack propagation. And finally, you are going to see the rough surface, all microscopic, right? That rough surface will tell that this is the final fracture region, right? You can correlate this with respect to your region 3, and that will be quite rough. Okay. And in the smooth zones, you are going to observe beach marks and striations. So beach marks, if you observe, those are macroscopic pair features. And if you observe beach mark, it means that load has changed during the service or there is some stoppage to the fatigue loading. Okay. And if you don't see any beach mark, that means, there was a continuous fatigue cycle going on, that to approximately say constant amplitude loading cycle. Okay. And then you will only see striations in those cases. And these striations are microscopic features. This also means if you have beach marks, there will be lots of striations in between. Okay. So say you are running a fatigue cycle, right? And for fatigue, during the fatigue cycle, you are forming lots of striations. Then you stopped it. So you are going to form beach mark and then you again started it. Then you again form striations and then you stopped it. So you are forming beach marks. So between beach marks, you are going to have lots of striations. Okay. That is what you can see in photographs. So let me draw some schematic. So if you have this surface, so this sample has a fracture, right? And you are observing the fracture surface. So there will be a very distinct initiation site. Say that the track initiated somewhere here. You can see actually when you see the fracture surface, right? And then you are going to see smooth surface, right? So it's something like this up to this point. There you are going to see lots of marks like this, all macroscopic. These are your beach marks. And finally, you are going to end up having final fracture, which will be rough surface. This is rough surface. Okay, and it is like catastrophic failure. And the central region between the initiation site and rough surface is your smooth surface. This is your smooth surface. Okay. So now if you see the top surface, or you have fractured the sample, you are not seeing the top surface, right? So somewhere here you are going to have initiation site, say it initiated here. Then you are going to observe beach marks. Okay, and finally fracture rough surface like this. Okay, so this is your rough surface. Final fracture. These are your fatigue propagation or fatigue track propagation. Smooth zone. And here your track has initiated. Okay, and what is your track direction? Propagation is growing in this direction, right? So this is the direction of track growth, right? So this is how your spectrograph is going to look like after fatigue failure. Okay? Now, depending upon the sample and alloy system, you can have either single fatigue initiation sites or you can have multiple fatigue initiation sites, right? For example, let me again draw some schematic. So if you see a spectrograph which is having a structure like this, where you have, and then this. Okay. So now you know that only single initiation site is there, which is this guy. Okay. And then what you see smooth surface and then the rough surface. So this is your smooth surface and this is your rough surface. And this is track initiation site. So this is the case of single nucleation site. Right? Now let's see what happens when you have two nucleation sites. So you have a surface or fracture surface. You're seeing from the top view. So you have now two crack initiation sites. So one is say here, another one is here. Now from both sides, you're going to have fatigue crack propagation. So say in this case, it grew like this. And in another one, it grew like this. And it is possible that one side, the crack propagation is much larger than the other side. So the situation could be something like this. And finally, you have a final fracture between these two propagation regions. Okay. So this is your final fracture. And then you have two nucleation sites, right? The blue one. So one is here and another one is here. So these are your nucleation sites, two nucleation sites. And the purple ones, those are fatigue track propagation region, right? Or smooth zone, which is fatigue track propagation. Okay. So if you look at the fracture surface, you should be able to distinguish it. You could have now multiple. You could have three or many more, right? And from all those sides, you are going to have crack growth. Some sides are going to from some sides the crack growth rate will be slow, and for other sides crack growth rate might be faster. And whatever is the remaining region, you are going to see final fracture. Okay, so this is how your spectrograph is going to look like after fatigue failure. Okay, so now let's understand what happens in Beachmark and striations. So I've already mentioned that there will be lots of striations between two Beachmark, right? So suppose I have a cycle which is going like this. And then I stopped it, okay, the fatigue cycle. And then I again started going. Then I again stopped it. Okay, then I again started growing, but then I increased the load. Okay, and then I stopped it. Okay, so you have 1, 2, 3, 4, 5, 6. 6 zone in a fatigue cycle. Just a schematic for understanding, right? So now out of these, which one will give you striations? So striations will be given by 1, 3, 5. See, eventually I am going to tell you how striations will form. Okay. For now, just realize that each cycle is going to give you one striation. Okay. So if I say how many striations are there in, say, region 1, it will be 4 striations. Okay. In region 4, also 3, it will be 2 striations. In region 5, it will be 6 striations, something like that. Okay, so depending upon number of cycles, you know what should be the number of striations. Okay, now Beachmark, it will be now region 2, region 4, and region 6 because we have stopped the test. Okay, now what could happen if I just draw the pattern or say fracture surface, how it is going to look like. So I can roughly draw something like this. So you are going to see striations. I will show you the striations also later on, so SEM images. So in region 1, you have 4 striations. Then you are going to see beach mark, which will be macroscopic. Okay. Then you are going to again see striations. Remember, striations are microscopic. Okay. Then again beach mark. But realize this is just a schematic for your understanding how these are forming. Okay, this might not happen in real situation. Typically you are going to have lots of number of cycles before you are going to stop it, right? Or before you are going to change the load. Okay, and then again, so this is 1, 2, then this small region is 3, then this 4, and then 5 is going to be more number of striations. 5, 6 striations. So this is regions 5. And then beach mark. Okay. So here the blue are beach mark and the purple ones are striations. Okay. Now, if you see, the number of striations are changing between 1, 3, and 5. That you know, because each cycle is going to give you one striations. We discussed that. In fact, if you see the loading amplitude or stress amplitude in 1 and 3, right? So although the number is changing, the gap between striations will remain almost same because the amplitude is same, right? But if you see number 5, the amplitude has increased. So the gap between the striations is also going to increase in region 5 as compared to region 1 and 3. Okay, and it happens because of the mechanisms by which striations form. Okay, so I hope you have understood, in its given fatigue cycle, how striations are going to form and when there will be beach mark. Okay, so striations will form in each cycle. The gap between striations will depend upon the stress amplitude. Higher the stress amplitude, the gap between striation will also be higher. Okay. So now let's talk about how actually striations form. Okay. And this is happening in stage 2, right? Okay. So there are two models we'll discuss. One is plastic blunting model, and another one is alternating slip model. Okay. We'll discuss one by one, both of them, so that you can understand it better. So I have a schematic. So this is for plastic blunting model. Okay, so if you see, I have shown here the cycle. So this belongs to A, then B, C, D, E, F. And all these points I have shown in a fatigue cycle. So you can see A, B, C, D, E, right? So C is at maximum load. A and B are during loading. So I would say, if I have a fatigue cycle like this, so this is loading and this is unloading. And this point is your maximum load, which is point C here. Okay. So what is happening at point A, which is the minimum load in a given cycle? See at the bottom, your track is closed, right? And this is your track. So this is closed. Okay. As you increase the load during loading cycle, you are coming to point B, right? You're opening the track. Okay. And what is happening? This activation of slip system is going to occur. Okay, in both the directions. So what is happening? Because of the activation of slip systems, dislocation emission will take place, which will lead to the material separation as I have shown here, right? So as soon as you reach to maximum load, you have a crack increment. You see, it has slightly increased, right? Okay. So now let me write down and then I will explain it for your better understanding. Okay. So this is plastic blunting model, which is process of alternate blunting and resharpening. of track tip. Okay. So during loading, blunting is going to occur. So blunting occurs during loading. So as we move from A to B to C, blunting of the track is going to occur, right? Which is track opening portion. And why it is happening? Due to significant slip emission, which causes material separation. Okay, so you are going to have slip emission, which is causing the material separation, as you can see here in both B and C, right? So here also you are going to see slip, right? So you are actually emitting dislocations, and because of that, you are causing the material separation. So at B, your track is very highly open, and then there is a slight increment also. Okay. Now, when you compress it, so on compression, due to slip reversal, the newly separated material at the track tip closes. So what is happening while unloading, because of the slip reversal, you are going to see the closing of the track tip. Okay, see here. So this is where closing start. Okay, so closing of track tip. And that is point D. And as you move further down to the minimum load, track has closed, right? And the track is now again resharpened. So you first blunted the track at point number C, which is the maximum load. And while coming back during unloading, you are resharpening the track, which is point number E in a fatigue cycle. Okay. And because of that, you are going to observe track increment, right? So this blunting and resharpening. So blunting is say point C and resharpening point E. Okay. There is an increment in track length. Okay. And when this happens, from going from point A to E, there is an increment in track length, and that step formation is striation. Formation of steps, which is called striation. Okay. Now this process is going to be repeated with number of cycles. So as you go to point F, your track again opens, there will be blunting, and it is going to reach to say point number G, and there will be track increment, there will be resharpening again during unloading, there will be again formation of striations, right? So for each cycle, you are going to get one step, right? One track increment, one step, So each cycle is going to give you one striation. And this is what plastic blunting model is all about. Okay. So basically it is blunting and resharpening of the crack tip, repeated blunting and resharpening of the crack tip. Okay. Now the another model is, which is I have shown here, is alternative slip model. So let me write down first and then I will explain. So under tension, slip emanates on a specific system, which undergoes work hardening. Okay. And because it has gone to gone for work hardening, the activation of another slip system is going to happen, right? So activation of another alternate. And that's why this is called alternating slip model. Okay. Slip system at the end of half cycle. So you are going to have the activation of alternate slip system at the end of half cycle. Okay. So let me explain this. So you have, say, this track. Now I am on the left side, right? And then you, because of the increment of during loading, because of the increment of load, there will be slip emission, right, on a particular slip system. So that particular slip system is, say, this line here, right? So dislocations are going to be emitted like this, right? Okay, and there will be track increment as I've shown here. So there will be increment and slight, there will be opening of the track and slight increment, right? So the dotted line now becomes the solid line here. So dotted line is the original line of the track, right? So now your track shape is something like this. So and that this particular slip system, say this is slip system is say 1. So in slip system number 1, work hardening takes place. Now it becomes very difficult for dislocations to move. So what is going to happen? There will be activation of alternate slip system at the end of the half cycle. That means if you have this cycle, so in the first cycle, say up to this particular point, to this point, you have activation of one slip system, and in another half of the cycle, there will be activation of number 2, which is here. Okay. So you are going to have dislocations in 2 also, right? And now your track becomes this. So instead of what we just discussed in plastic blunting model, that on both the slip systems, you have a slip emission taking place. In this alternative slip model, it predicts that no, it is the first slip system gets activated and work hardening takes place, and then activation of another alternate slip systems occurs at the end of the half cycle. Okay. Now while unloading now, so during compression, the slips from non-hardening system completely returns to the crack tip, that is reversibly, and nullifies the emission generated collective slip steps. Okay. However, the dislocations on the work hardened slip system, that is irreversible. Okay, so this guy here is irreversible. And say this one is reversible. This is work hardened also. Okay, however, dislocations from work hardened system remain as residual product. That is irreversibly. And when this happens, there is a extension, crack extension along the perpendicular plane. So this causes crack extension along that perpendicular plane. Okay, and the whole process is repeated and striations are formed. Okay, so what is happening? You have work hardening in slip system 1. So slip system 2 gets activated. Now the first slip system that is irreversible because it has already work hardened. Okay. So in slip system 2, you have reversibility, right? Slip reversibility. That is what I have written here. So during compression, the slip from the non-hardening system, which is slip system 2 here, completely returns to the crack tip and nullifies the emission generated collective slip, right? So you can imagine that, because of the slip reversibility, it closes, right? The crack which opened because of the slip emission in slip system 2, it closes back, right? And that leads to the for extension of crack, right? So instead of both the slip systems getting activated as we had that in blunting model, here one slip system get activated first and then alternative slip systems get activated. That's why the name is given as alternating slip model. Okay. Again, in this case, each cycle is going to give you one striations. Okay. So if you have n number of cycles, we will expect that there will be formation of n number of striations. Okay. So we have now completed the topic of fatigue. Okay. I will show you now the schematic as well as spectrographs and extrusion, intrusion, all SEM images I will show you because I had drawn initially the schematic. Okay. So it will now help you understand better. So let me go one by one. So the first here is stage 1, stage 2 growth in 3D. Okay. And then striations model, what we just discussed, that also you will see in 3D. Okay, so it's a paper by P. Chaudhary, Mechanisms of Fatigue Crack Growth, a Critical Digest of Theoretical Development. Okay, and if you see here, it's a very nice paper, right? You can go through it also. So this nicely shows this 3D image here. You know, the crack initiates from the extrusions on the surface, intrusions on the surface, right? And you can see grains. So the stage one, which is in red color, these are what? Crystallographic in nature, right? The crack path is crystallographic. We have discussed that. And that is what you see here, right? The crack path is crystallographic in stage one. And as soon as it enters stage two, which is the blue region here, it becomes the crack propagation becomes perpendicular to the direction, loading direction, which is shown here, right? So it is almost perpendicular to the loading direction. Okay. And what you see here, you know, something like this. These are striations if you talk about the macroscopic scale. Okay, so it very nicely shows the 3D image of what we have already discussed. Now this is again another one. So what you see here, this is AFM image. So on the surface, you can see extrusion. Okay, these are AFM images. Okay, and then these are your crystallographic nature of the crack plane. And then you see a flat of approximately flat region which is perpendicular to the loading direction. And these are striations. If you see the electron microscope image, these lines, these are striations. I will show you more images of striations, right? Very fine ridges on the surface. And each striation will correspond to one fatigue cycle. We just discussed about that. Okay. Now about the models. So this is the plastic blunting model, 3D view. You can nicely see, right? So you have this crack, you are opening it. So crack is getting blunted because of the emission of dislocations, right? And while unloading, you are again resharpening the crack. And in this way, you are actually going to increment the crackling. Okay, so you can see crack position was initially here. Now there is extension of the crack, right? Now this is the alternating slip model. So you have this crack which is in blue. So one slip system is getting activated in half of the cycle. Now it gets wort hardened, then another slip systems get activated, which is here, which is written as easier glide, right? And during unloading, you are going to close the easier glide emission, right? Which has already occurred. And that will lead to the extension of the crack. Okay. And this process is going to repeat again and again. And for each cycle, you are going to form striation. Okay. So this is the one I was talking about. Okay. So now let's go to another image. Stage one crack growth. So this is paper by Zhang. Okay. And if you see here, let me go to the title first. So this is paper of Zhang in MSCA published in 2019. And you can nicely see stage one crack. Okay, so this is the crack one initiation. And this is the slip lines you can see. And this is the crack. Okay, and this is the slip system written in red. So the crack propagates in this direction after 2799 cycles, right? Then it changes the direction to another slip system at 2833 and it propagates in that particular grain, right? Then it again changes the direction in 3132 cycle, right? And this process goes on like that. So this is stage one crack growth where the crack path is crystallographic in nature. Okay, so in a particular system, you are going to see crack propagation, right? Now let's go to third one. So striations, right? Fatigue striations. So these are your striations. This is one of the images, right? Striations. I have better image here. These are also striations. Okay? Okay, this is what I wanted to see. So see on the right side, here I have shown, so these are your striations, right? And see the scale bar, 10 micron. This whole length is 10 micron. So very, very fine ridges on the surface, and each will correspond to one cycle. Okay. On the left side also, you can see striations. Okay. So here you have overstretched fracture. So this is your fracture region, right? Somewhere here your track might have initiated. So you see smooth zone here, which is striations and fatigue preparation. Somewhere here crack might have initiated. And then you see the fracture region, which is rough surface. We discussed that. Okay. Now next one is extrusion and intrusions. Schematic. So this is the paper by Sakai in International Journal of Fatigue 2016. And this is the striations. Sorry, extrusion and intrusion schematic. So I had drawn it. I just wanted to show you nice schematic. Okay. So you can see these are your striations and these are, again, sorry, these are your extrusions and this is your intrusions. And then you have persistent slip band, which is a ladder structure of dislocation. So these are your persistent slip bands. So here in the slip bands, you're going to see lots of dislocations in the form of ladder structures. Okay. Now, actual image of extrusion and intrusions. So this is a paper by Pollack in Material Science Engineering 8 and 14. So you can now see here. So you can see intrusions, you can see extrusions, see the scale bar 200 nanometers. Okay. So in these intrusions, you have initiated the fatigue crack. This is example 1. These are your intrusions and extrusion in AFM image. Okay. Now let me see another one if I have here. You can see extrusion and intrusion here also. Okay, there is nothing here. So let's go to another one. So this is a paper by again Pollack in Willy Online Library. A profile of persistent slip markings and internal structure of underlying persistent slip bands. So let me show you the image. Okay, so you can see here 1 micron, this is your intrusion, this is your extrusion on the surface, and this is the crack growing from the intrusions, right? Again here you can see extrusion, then intrusion, again extrusion, intrusion, extrusion, intrusion, and from the intrusions you are growing crack. This is what we discussed, right? Okay. Here you can see persistent slip bands. So this is your persistent slip bands. You can see these dislocations. Okay. And from there, you are seeing this region which is going out. The extruded one, this is extrusion, this is intrusion, right? This is extrusion here, again intrusion, then extrusion and intrusion. And you can see persistent slip bands here. Okay. Again here you can see extrusion and intrusion. So there are lots of images available in the internet also. Okay. Now Beachmarks. So we know striations, those are microscopic images. You saw the scale bar. Okay, now let's see Beachmark. So this is an open access paper from Mura, Investigation of Fatigue Behavior of ABS Polymers. So these are your Beachmarks in polymers. Okay, you can see macroscopically you should be able to see. So these are your Beachmarks. Okay, let's go to another one. Okay, so here you have two tracks initiation. We had discussed. So track 1, initiation site, track 2, initiation site. Okay, and then it is going to grow. So you have these Beachmarks. So you see these lines, which is not clearly visible, but you can see actually these are lines. Macroscopically, you are able to see these lines, right? So these are your Beachmarks. Okay. Now one more paper. Again, open access, fatigue failure analysis of a speed reduction shaft. So here, if you see, right? You can see these lines. So these are your beach marks. Okay. Somewhere here crack nucleated and you see this smooth region. So this is your fatigue crack propagation region. And these lines, whatever you see macroscopically, see the scale bar, 15 millimeter, right? So these lines, macroscopically, these are your beach marks. You can clearly see here your crack initiated and this region is your fatigue region. And then you have fast failure here, rough surface. Okay, so the fatigue region is marked in yellow, right? So this is your fatigue region. And here it is your fast fracture, okay, or final fracture. Now let's see crack initiation sites. So this is from Xiong, okay, published in 2021. Okay, so let's see that image. Okay, here. So you can see these images, right? So here crack has initiated. So there are three initiation sites, 1, 2, 3, and the crack is propagating. Here also crack initiation site is there, right? So if you see the image, you should be able to figure out where crack has initiated. Okay. Now this is another one. So this is a very nice image, right? So you can see this is a smooth surface, right? And this is the rough surface. So here you have fatigue crack propagation and then final fracture has occurred here, right? Now this is your crack initiation site. Then again, here is your crack initiation site and here is your crack initiation site. Okay. So this guy here is your rough zone. Okay. And you can see these beach marks. Another paper. So I'm showing you lots of images so that you can understand the concepts. Okay. So here, if you see this particular image, so this is your smooth zone, right? So this is your fatigue zone and this is your fast fracture here. Okay. Now another one. So this is the paper by Deng, published in 2019. Okay. So if you see here, okay, so this is where crack initiated and this is your fatigue crack propagations region and the white one here is your fast fracture region. Okay. Okay, so the last image, if you remember, I told you that I'm going to show you the schematic of coffin mention and basking, right? So this is what I have. This is from Adam paper, International Journal of Fatigue 2008, and this is the image, right? A nice schematic I drew before, but I told you that I will show you also, right? So you have this black curve and the blue one is your basking relationship and the red one is your coffin mansion relationship, right? If you remember, so equations are also given. So if your strain is higher, then coffin mansion is going to be valid and at lower strain, your basking equation is going to be valid. That is what we discussed. Okay. So we have completed a topic of fatigue, especially for alloy systems. I'll stop here and we'll meet in the next lecture. Thank you.